Hello everyone, welcome to my programming club. Today we will be solving another daily Leetcode problem, and the problem's name is partition array for maximum sum. So the problem statement goes like this: given an array ARR, partition the array into contiguous subarrays of length at most k. After partitioning, each subarray has their values changed to become the maximum value of that subarray. Return the largest sum of given array after partitioning, and it is to be noted that test cases are generated so that answer fits in a 32-bit integer. Okay, so let's have a look at the constraints. So constraints here are that the length of the array will be of order 10 raised to will be of order 500, and each element of the array is of order 10 raised to power 9, and length of the array is either greater than equal to a value of k that will be given to you. Okay, so k is the maximum size of the subarray that can be there. So let's see how we'll be solving this particular problem. First of all, what we can do is we can apply a brute force approach. This is the first approach that will be coming to our mind. So what we can do is, let's say this is the array given to you. Let's mark the indices. So for each index you are having two options. Either to apply the partition here or not to apply the partition here. Okay, either to apply partition here or not to apply partition here. So in all, for every index there will be two choices, so the number of choices will be something like this, and it will be repeated n number of times, where n here is the size of the input array. Okay, and overall order of number of operations will be 2 raised to power n. N here is given to be, as you can see in the constraints, of order 500. So 2 raised to power 500 is a pretty huge number of operations. These number of operations will be required to generate all possible partition combinations. Okay, generate all possible partition combinations. Okay, and it is very much greater than the limit of operations, which is 10 raised to power 8 operations. So these are the number of operations limit. Basically, if the number of operations required by a program to solve a particular problem, these are the number of operations required by a solution. Basically, if this value exceeds 10 raised to power 8 operation limit, then your solution may not be getting accepted, or even if it reaches to this limit, then your solution may not getting be accepted, and it will be getting TLE, time limit exceeded, and it will not be accepted. So this brute force solution needs to be optimized. Okay, optimization is needed here. Okay, so let's make few observations about this particular problem, then we will be proceeding to the optimization. Okay, so the first observation is, let's say you are starting at the very beginning, the very first index that is there, and you go on making some set of choices. Okay, let's say after some set of choices you end up at an index I, or let's say index. Okay, this was the 0th index, and there is another set of choices. So this is what the recursion tree will be looking like. Okay, so there is some another set of choices which is also leading to this particular index, and you are applying a partition at this particular index. Okay, so in both of these cases you will be doing some extra work. Why? Let's say it is the first combination that is there, then let's say there are 3 other combinations branching out after you have applied partition here. Okay, so same 3 combinations will again be branching out from here also. Okay, these 3 combinations will again be branching out. So as you can see that this part is being repeated more than once. Okay, so if you would have stored the result of this particular part somewhere, then you need not to do extra work. Okay, so we can save some extra work here, and this particular property of subproblems being repeated, this is kind of a subproblem in itself. Okay, so if you consider this index as the beginning 0th index, this is a subproblem in itself. So this subproblem is repeating in more than one combination. Okay, so this particular property of a problem is called, first property is overlapping subproblems. Those of you who are new to this particular property, I will be providing a link of an article where this particular property will be explained. You can explore that article and then you will be having a better understanding about this. Now let's come to the second property. So second property is, let's say you are at a particular index, then I may ask that if let's say your array is ending here at this index and this is the last partition that is there, so what is the maximum sum that you can achieve if let's say the partition is ending here? What is maximum sum that you can achieve if the partition is ending here? Or you can say it is your array's end. Okay, so it will be entirely dependent on what are the partitions previous to this and what are their placements that you have done. Okay, so we can say that solution of bigger subproblem can be derived by combining the solutions of smaller subproblems. Okay, these are smaller subproblems. So this these are affecting the solution of bigger subproblem, and they can be combined to form the solution of bigger subproblem. Okay, let's call them solution 1 2 3. Okay, so this kind of property is called optimal substructure. Optimal substructure. So for those of you who are new to this particular property also, link of another article will be provided here for this particular property also, and after you are done exploring that article, you will be having a better understanding of this one also. Okay, and if a problem satisfies these two properties, then a optimization technique can be applied here, which is dynamic programming. Okay, dynamic programming. Those of you who are new to this particular approach or optimization approach, I'll be also providing a link of an article describing what dynamic programming is, so you should definitely check that out if you are new to this concept. So what happens here is, when we were doing this extra work, what we will do now, we will store the result of a subproblem when it is encountered for the very first time. Okay, let's say we stored it somewhere. Okay, the result is stored here. Now let's say when you are encountering the same subproblem again, then you will not do the recursion or calculations again. You will just refer to this result and return it. Okay, okay, so that's how you will be saving some extra work. Okay, so we store the intermediate state or subproblem results, and save some extra work. When these states or subproblems occur again. And other thing that we'll be doing here is, we will be using these intermediate state results to form results for bigger states. Okay, results, or you can say solution. Okay, that is based upon entirely on your preference. So this is in a nutshell what dynamic programming is. Okay, now let's see how we will be implementing or applying dynamic programming over this particular problem. Okay, now let's say you are at a particular index. Okay, now let's see, this is the index where we are applying ending partition for the current segment. We are applying ending partition for the current segment. Okay, at this index. So how long that current segment can be? It can be as long as k length. Okay, if you include this one also, this can be at most k length. Okay, it is mentioned in the problem statement, then each segment can be at most of k length of at most k. Okay, uh, so after that there should be another segment, or let's say if it is the very first segment, then there will not be another segment. For now, for simplicity, we are assuming that there should be some other segment. Okay, let's call this previous segment. Okay, so if you consider this as a slider, okay, so this is a slider. You can place this slider anywhere here. Okay, so size of this particular segment, which is our current segment by the way, can be decreased. Okay, it can be decreased from k to 1. Okay, so this particular segment can be from 1 to k length. Its length can be differing from that. So we will try to move this slider at different positions and see what will be the optimal position of this slider. Okay, so now once we have find out what is the optimal position of this slider, this will automatically give us result for what will be the sum, maximum sum possible if your array is ending at this particular index. Or in other words, you can say that if what will be the maximum sum possible if we are placing the ending partition at this particular index. Okay, so looks like we are having a transition equation. What that transition equation be? First of all, you should be knowing that how many variables are there which are determining the current state, or the, okay, so there is only one variable that is determining the current state, which is index. Okay, so at what index you are placing the ending partition for a particular segment. So there is only one state variable. So in total, how many dimensions of an a data structure, or let's say array or vector, that will be required to store the results of intermediate states will be there? Only 1D DP will be required. DP is dynamic programming. So one dimensional structure will be sufficient since there is only one state variable. Okay, so let's call this structure as some state. Some state at a particular index will be nothing but previous segment can be also differing. Okay, last previous segment contribution plus whatever will be the maximum number in this particular segment, that is your current segment. This is your current segment. Let's say x is maximum here, so max till now you can say, or max in segment, max in current segment. Into length of current segment. Okay, that many number of times current maximum number will be repeated, and it will be generating sum for the current segment. Okay, so seems like we are having a state transition equation here. So this will be the state transition equation. Now this length of current segment will be determining what your previous segment will be and what will be the contribution of current segment. Okay, so let's see the implementation. So this is the implementation. First of all, this sum state will be used to store the results of intermediate states, and then using those results to build the states of bigger states. Okay, and avoiding extra work also. So it will be a two-step process. You will be avoiding extra work and using the solution of smaller states to build the solution of bigger states. So it will be used for storing the results of state. Store the results of states. Let me zoom out. Okay, and build solution or say result of bigger states from smaller state results or say solutions. Okay, so then we will be populating our state array or vector. By using state transition equation. So this is the part where we are moving the slider and using the state transition equation. This is the part where we are moving the slider. Slider is just a partition, imaginary construct it is. Just introduced to make you understand how this will work. Okay, so length will be differing from 1 to k. Okay, so this particular index can be as far as from current index, which is this index minus k minus 1. Okay, since we are including index also. So starting from the current index, your previous index, this is your previous index, by the way. Let me remove some part. Yeah, I guess now it's fine. So this is the previous index, and this is your current index. Okay, so this previous index can be ranging from starting from the current index, which is this index, till here, your current index minus k. It should be greater than that. And we will be constantly decrementing. We are just trying different positions of slider. Okay, moving the slider to left, starting from current index. Okay, then we will be seeing what is the maximum element in the current segment. What is the maximum element in the current segment? Okay, so whatever will be the maximum element in the current segment, and then we will be multiplying it with the segment length. This is nothing but segment length. You can replace it with segment length. You can declare a variable here. Okay, so this, depending upon previous index minus 1, whether there is some segment before the current segment or not, you will be adding the contribution of previous segment. Okay, so if you want, you can separate it also, and you can name it to previous segment contribution. Let's separate it. So previous segment contribution. Okay, and if you want, you can separate this one also. Current segment contribution. Okay, and we will keep updating the value of some state. Okay, so some state, if you may ask, is nothing but what will be the maximum sum possible if we place ending partition at a particular index. Okay, and then you will be returning whatever will be the sum state at the very last index, since last index will be the index that will be definitely used, okay, for the ending partition. And that is how we will be solving this particular problem. If you are still having any doubts or any queries in general, then please feel free to ask them in the comment section. Thank you for watching. Have a great day ahead.